Hello and welcome. This is chapter number 12, three-phase circuits of our Sadiku's textbook. Let's start. So the first topic of this chapter is single-phase circuit. So a single-phase circuit or a single-phase AC power system consists of a generator connected to a load through a pair of wires. So here below we have a diagram that shows this thing. We have this section as a single phase generator or source that is connected to a ZL or a load via these wires. So these are our wires, or in terms of power systems, these are transmission / distribution lines. Okay, so always when we have to connect a power source to a power load, we have a power source, we have a load, and we have the connecting wires. So if if we have to draw a single line diagram of such a case, that case will look something like this. Remember why this thing is called a phase, because we know that, or we have seen earlier in our lectures, that voltage is generally given as V times, so for example, Vm cos of omega t plus y. This is, for example, our voltage, and this is in time domain. And what will be the phasor of this thing? Or I call it as Vp. The phasor for this thing, or the phasor for the above voltage value, will be Vp magnitude angle of phi. And since the power systems are working on constant frequency, they have a constant frequency that is omega equals to constant or f equals to constant. So they have a constant operating frequency. So we can easily convert our time domain signals to phasor domain, and we can use that phasor domain to solve our circuits, and this technique makes our life much easier, because solving in time domain, and that too AC power systems, is seriously complicated. So this is how a single phase circuit diagram looks like. Next part, single phase 3-wire circuit. So remember, now single phase circuit, which we have seen in our previous slide, is a very basic way of connecting a power source to a load. But in practical cases, we have multiple connection or connecting schemes. We can connect single phase with multiple wires or multiple wiring systems. Similarly, we have polyphase networks, and we can connect them again using multiple wire circuits. So here we are talking about a single phase 3-wire circuit. So it says it is a more common practice to have a single phase 3-wire system. So if you are living in North American continent, you will be accustomed to seeing something like this. So there we have most of our systems or our domestic wiring. You can find this sort of arrangement inside the house, where a single phase is coming from the transformer, and that single phase is given to your house in this manner. So remember, it consists of two identical sources of same phase and magnitude connected to a load as shown. So this is our load, this is shown. So it's just like having two identical single phase networks connected to a single neutral line. The load connected to a source via two outer wires is a neutral wire. So this is our neutral wire from N to N dash. Remember, N dash is the neutral wire. So this is your neutral wire. So examples, remember, a normal household system is a single phase 3-wire system, because the terminal voltages are because the terminal voltages are the same magnitude, are of the same magnitude and same phase. So these terminal voltages, the magnitude is same, that is VP, both are the same, and theta is the phase. For both these cases, the terminal voltage is the same. And what also it does, it also allows us to connect both 120 and 240 volt appliances. So for example, if we have a load that is working or on 120 volts, we can easily apply this on 120 volts. Generally in North American continent, we have 120 volt phase coming, unlike the Indian subcontinent where we have 240 volts single phase. So we have 120 volts available, 120 volts available. So if we have for example, in the same network, we want to connect a load that is operating at 240 volts, just connect that load between A and B. For example, something like this. So you can take a terminal from A and you can take a terminal from B and then connect to Z load. And say this load operates at 240 volts. So you can easily operate appliances that require 240 volts, and you can also use the same thing for 120 volts as well. Next case is a two-phase three-wire system. So actually, or in practical systems, we have, or the supply that is available to us in our domestic household or in our industry is of three-phase circuits. So therefore, polyphase circuits are of uh, important, of we can say of prime importance for us. So in case before we go to phase three wire circuits, there is a line. It says in your textbook, it says circuits or systems in AC which AC power source operate at same frequency but different phases are known as polyphase circuits. So initially, when the engineers developed some generators, uh, they came up or they developed single phase circuits, and when then that generator technology evolved, it went to two phase circuits and then three phase, and even they have developed multiple phases, more than three phase as well. But those generators didn't worked as they would have thought they would work, or there were serious challenges in operating those generators. So eventually they settled down with for a three phase. So anything or any circuit that is operating in more than one phase is a polyphase circuit or example of a polyphase circuit. So if we have two phase, three wire system, so it is an example of a polyphase circuit. So in this circuit, so we are shown this diagram. So it is much similar or much similar to the previous diagram of single phase three wire circuit. The only difference is this phase and this phase. So the sources we have over here, the phase of source 1 is 0 degrees, the phase of source 2 is minus 90 degrees. So basically these two sources are supplying voltages that are 90 apart from each other. So how the two phase three wire circuit look like? So it has a generator of two coils that are perpendicularly wound to each other. So then we have two voltages are generated in these coils, and the voltages have a phase difference of 90 degree with each other. So you can we can from the on a machine's perspective, remember generator consists of a rotating device, or we call it a rotor, and then generator has a stationary component or a stationary section that is called a stator. I will write it as a stator. So the stator or the stationary component contains or consists of a soft iron core or a conducting core, not a conducting core, but of an alloy that has the winding wound on it. Similarly, the rotor is of magnetic material that rotates, because that rotor is actually connected to a turbine, and that turbine rotates because of anything, because of in say diesel power plants, it may be rotating because of the uh, steam pressure, or in a hydroelectric power plant, the turbine may be rotating because of the pressure of the water on its blade. So that turbine is connected to a rotor, and that rotor rotates inside the stator, and there the windings are present on the stator, and those windings are actually or physically 90-degree apart from each other. So the rotor, when it rotates, and rotor is a magnetic material, and if there is a magnetic material that is rotating in the vicinity of conductors which are connected to a circuit, so there is rate of change of magnetic flux across those conductors, and that generates EMF because of the Faraday's law of electromagnetic induction. And once that EMF is generated, we can just capture that EMF and transfer it to our load with the help of these transmission or distribution lines. Okay, so this is what it is happening here. Then we have three-phase circuits, or the three-phase circuits are the polyphase circuits, which are most common uh, to us, and we use them extensively in our daily life, or in the the power systems we have, or the electricity coming to our homes for various power plants, whether they are renewable based power plants or whether they are non-renewable based power plants. They generally operate on three-phase systems. So remember, AC source voltages have same frequency and amplitude. So what the generators which are generating these voltages, they are generating it at a certain frequency and they have a fixed amplitude. The AC source voltages are 120-degree apart. So all these three-phase voltages, for example, we call them VA, VB, and VC. So there will be 120-degree difference between these two, and there will be 120-degree phase difference between these two voltages. They, Again, the most commonly used across the world, so three-phase circuits or three-phase power systems are the ones that are used extensively across the world. Remember that one of the key advantages is the instantaneous power is constant in three-phase systems, and it is not pulsating. So instantaneous power is not pulsating in three-phase systems, unlike two-phase or single-phase systems. Then generation machines have less vibrations in three-phase systems. This one, again, this is another important aspect which led to the development of three-phase generators, not five-phase, seven-phase, or more than that, because of these physical challenges which came up with that. Then economical for the same amount of power transmission compared to single-phase systems. This is another important aspect. The amount of conductor that is required to transfer same amount of power. Say for example, if we have to transfer 1 megawatt of power from a generation station to a locality, uh, we need certain amount of conductors, and generally these conductors are made up of aluminum or copper. Uh, and in order to have efficient transmission, we need, or more than efficient, I would say economical transmission, we need to have, or we need to reduce the amount of material that is used in these conductors, because copper or aluminum are expensive materials. So we do not want to spend a lot of money on to in developing or in fabricating or in making these transmission line or distribution line conductors. We need to have a very economical way of transmitting 1 megawatt of power from one end to the other. So if we have three-phase systems, and if we have a single-phase system, a three-phase system will be more economical as far as conductors are concise, or concise of conductors is concerned. Then less wire is utilized in three-phase system compared to equivalent uh, single-phase systems. Yes, this is another advantage um, uh, of using three-phase circuits. So again, one thing to remember, there are different textbooks that are available, and they are written by multiple authors. So if you remember reading a book that is written by a North American authors, remember with North America, we have Canada and United States with them. So they are operating on 60 hertz of frequency, that is 377 radians per second. Similarly, if there is an Indian or a Pakistani or a Bangladeshi or a Sri Lankan textbook that is available to us, or for that matter, a British textbook that is available to us, they are operating on 50 hertz of frequency, and that is 314 radians per second. Okay, and remember, omega equals to 2 pi f. Omega is the radians per second, f is the hertz we have. Okay, so how a three-phase circuit single line diagram looks like? A three-phase circuit single line diagram looks something like this. So we have phase A connected with the neutral, phase B connected with the neutral, and a phase C connected with the neutral. Similarly, the load between load connected to phase A to neutral, phase B to neutral, and phase C to neutral are given as ZL1, ZL2, ZL3. uh, Similarly, the voltage source at phase A, that is between phase A and neutral, that is VP angle of 0. The voltage at phase B, VP angle of minus 120, and voltage at phase C is VP plus 120, or it can also be called as VP angle of minus 240 degrees. Okay, but remember, there is a convention, or generally the textbook, they keep the angles between 0 and 180 degrees. So they could have written as minus 240, but it's a good way of writing it between 0 and 180 with a plus and a minus sign. Okay, so both angles are same, and this is because of the symmetry of the angles they repeat after these trigonometric angles after half cycle, or 180 degree rotation. So moving ahead, this is something which I was talking earlier. Here we can see a figure of motor. So, but let's say, so three-phase generators are used to generate three-phase AC voltages. So as I have talked earlier, that for two-phase generation, we have a generator that have two-phase or two different windings that are 90 degree apart, and there is a stator which will have those windings, and there is a rotor that is rotating inside a stator. And uh, once the rotator starts rotating, EMF will be produced. So here, for three-phase circuits, we'll have uh, three different phase voltages are generated: VA and neutral, VB and neutral, or VC and neutral. So these voltages, remember, are always balanced if the amplitude or the magnitude of all these phases, like VAN equals to VBN equals to VCN. The magnitude or amplitude of these phases are equal, then, and also the frequency must be equal. So omega slash F must be the same for VA, VB, VC. And these phases are 120 degree apart from each other, VA or VB and VC. So remember, as I have said earlier as well, the generator consists of a rotating magnet or a rotor and a stationary winding, that is a stator. Uh, so there are three separate windings on the stator. So we have three separate windings. So winding A dash is one winding, B dash is one winding, C dash is a one winding. Or you can consider it as a loop of consolidated copper coils. So they are rotated, or they are wound on this stator. So this is coming. So this is a cross-sectional diagram. So this wire basically comes over here, goes down, and this is the back side of this. So it comes here, goes over, and then goes back. So it's a complete loop, and they are physically. So the angle between, if say this is a complete 160 degree, so the angle between B, so angle between B is 120 degree. Between B and C, is again 120 degrees. So these are 120 degrees apart. So again, C and A is 120 degrees. So A dash, B dash, C dash. This is the return path. So these are, so similarly B A, B, C. If we want to say this is the physically 120 degrees angles between A, C, this is 120 degrees between A and C. And A and B is again 120, and B and C is 120 degrees. And that basically gives the 120-degree phase difference when the voltages are generated uh, uh, by after or once the rotor starts rotating. So again, it says third point, rotors rotates inducing voltages in the stator coil. Again, as we know that rotor is a magnetic material, and if we know that if a magnetic material is rotating or is moving in the vicinity of conductors, there is induced EMF or electromotive force or voltage inside the conductor, and that induced voltage is because of the Faraday's law of electromagnetic induction. Okay, so this is how these voltages looks like in time domain if you are going to draw the voltage signals. So first voltage starts from 0 degree and going like this, then VB will be 120 degree apart. It will start after 120 degrees or 120 degree of phase difference. Similarly, VCN will start after 240 degrees. And this you can say combination may change as well, uh, because for example AN is starting like this, then B, instead of BN you have uh, this is say for example 240. So instead of BN, we can have CN starting like this. So this can be VCN, VAN, and then your B may be starting from here as well. So this may be your BBN. Again, this is up to the way, the convention in which the windings are attached, or the way the engineers or a power system guys over there assign certain phases to certain outlets of the generators. So this is up to them, and we'll see ahead that this thing is called the phase sequence. So ABC is a phase sequence, ACB is so ABC is a phase sequence. So first A phase, then your B phase is coming, then C phase is coming. So here you have first A phase coming, then C is coming, then B is coming. So these are phase sequences uh, uh, over here. And again, it depends upon the nature of our power system, or the power system engineers or the designers, in which the way they assign these phases based on their generators or their systems requirements stuff. So uh, how these phase sources are connected. So there are two ways in which these three phase sources can be connected. So on a generator, when these three phases are generated, they can be taken out in a Y connected fashion. So they can be taken out from a generator in a Y connected fashion, where you have a neutral wire, and each phase is with respect to the neutral, AN, BN, CN, and you can always have AB, BC as well. So voltage between AB, BC as well, and you can always have voltage between AN as well. Similarly, it can be connected in delta fashion, where you have only, you do not have a neutral wire, you have only the voltages AB between two phases, AB, BC, and AC. So you have three So again, there are advantages and disadvantages of each of these connections, and we will see earlier that that how this sort of connection can be converted to a delta connection, and this sort of delta connection can be converted to a Y connection, and how we use these different mechanisms to inter converting to each other, and to solve for different combinations of load attachments to these three-phase sources. So again, note that we shall be using Y connected circuits for discussion unless until specified. So this is one thing that your book is talking about, that whenever your book gives an example or talks about something, it considers that they are talking about, or we are talking about Y connected system, unless until specified. So if there is a question, or if there is some discussion specifically related to delta connected circuits, they will be specifying that yes, this is now we are talking about delta connected circuits. Okay, so again, balance three-phase voltages. So for example, and I think I have gone through this point earlier as well. So let's see this point over here again. For a Y connected system, say for example, let us assume a Y connected circuit. We have VAN, VBN, and VCN are the voltages between the lines A, B, and C, and the neutral. So between line A and neutral is VAN. Between say line B and neutral is VBN. Between line C and neutral is VCN. So if these voltages have same magnitude, that means that VAN magnitude is equal to VBN magnitude is equal to VCN magnitude. It means that and frequency of VAN is equal to frequency of VBN equals to frequency of VCN. So this is BN, and there is 120-degree phase apart, means that theta AN is say for example 0 degrees, theta BN is 120 degrees, and theta CN is minus 120 degrees or 240 degrees, depends upon the convention, or it can be anything, something like this. So in this case, it means that we have a balanced three-phase source, or we have a balanced three-phase voltage. So balanced three-phase voltages or a balanced three-phase source. Okay, so this is also a terminology that is used in the literature as well. So moving ahead, so a balanced three-phase circuit, there are two possible combinations of phase voltages. One is called positive phase sequence. The other is called a negative phase sequence. So remember this slide where I was talking about the way or convention in which these voltage phases can be extracted out of the generator. So they are called phase sequences. So if we have A coming first, then B coming, and then C coming, means it's a positive sequence. And then if we have A coming first, then C coming first, and then B coming first, it means that we have a negative phase sequence. So phase sequence, it is the time order in which the voltages passes through their respective maximum values. Okay, so let's see about them. So for example, a positive phase sequence, it is something like this. So if we draw the phasors and start rotating this phasor in a counterclockwise or anti-clockwise rotation, then and we start, say this is the x-axis or the horizontal axis. Horizontal axis, and see which vector is cutting this horizontal axis when we are rotating it anti-clockwise. So for example, so if the an is at 0, so first if we start rotating, vector b will cut this, then vector c will come, then vector a will come again, then b will come, c will come, a will come, then b will come, c will come, a will come, and so on. So here we can see that the repeating pattern is ABC, ABC, so on, so forth. So this is ABC, ABC, ABC. So this is a positive phase sequence. Then if we are going to write down these phasors, so VAN, this phasor can be written as VP angle of 0. So this is VP. So remember, these values are RMS values unless until specified, until specified. So all these values are RMS values, VP, these are given in RMS values. So these are not peak values, these are RMS values unless they specify it. Okay, fine, that you are going taking the maximum amplitude. So this phase vector or this phasor of VN is VP angle of 0, then VC. So if we are going to write this phase vector, this phase vector is VP angle of uh, you can call it as 120 degree, or we can call it as VP angle of minus 240 degrees. Okay, both are fine. Then VBN, so VBN we can call it as VP angle of plus 240 degrees, or VP angle of minus 120 degrees. So remember the convention that we cannot, or we usually make sure, or we like to keep our angles between 0 and 180. So this is how, or this is why the key convention you will be seeing in the textbook is this angle, or this angle. And your textbook basically shows you that yes, you can write it as minus 240 degrees. There will be no issue in that. But a good engineer will write the values in this fashion. Then moving ahead, now what or how a negative phase sequence will look like. So all we can see from this diagram and the previous diagram, that here we have VCN and we have VBN here in positive sequence. The only thing that changed is the phasor value, or the angles, or the phase locations of the phase B and C, while one phase remains constant. So here again, say this is our horizontal axis, so x-axis. If we are going to see, or so if we have to determine the phase sequence, say if we are not told what phase sequence it is, so and this is again rotating in counterclockwise direction, or anti-clockwise direction. So first we can see that vector C or phasor C will cut this x-axis, then vector B will come, then A will come again, then C will come, B will come, A will come, CVA, CBA. So we can see our if A is our reference, so we can see that ACB is one pattern, then we have ACB, then we have ACB, and so on and so forth. So ACB, ACB, ACB dot 8. So this is a negative phase sequence. So in negative phase sequence, if you are going to write the phasor values, again VP angle of 0, VBN again VP angle of plus 120 degrees, and VCN VP angle of plus 240, or VP angle of minus 120 degrees. So again, a good convention, keep your angles between 0 and 180. So VC is this, VP is this, VA is this. So here what you can see, VC minus 120, they can also have written as VP angle of plus 240 degrees, but it's up to them. Okay. So now coming to loads. So we have, as we have seen, that our sources can be connected in delta combination or can be connected in Y combination, like these. So similarly, our loads can be connected in either delta combinations or Y combination. So here in this diagram, we can see that our loads are connected in a Y combination. So we have Z1 impedance that is connected between A and neutral, between one phase. Between B and neutral, we have Z2 or impedance 2, and we have impedance Z3 between C and N. So remember, a balanced load is one which in which the phase impedances are equal. So if we have Z1 magnitude equals to Z2 magnitude equals to Z3 magnitude, and the phase, so Z1 phase 1 equals to phase 2 equals to phase 3, then we can say that these all three phase load is a balanced load. So remember ZY, so we can also convert it into ZY, and ZY generally is a single phase load impedance or load impedance per phase. ZY is generally in per phase. So if this thing is balanced, it means that phase, so we have three phases. Phases are AN, BN, and Cn. So these are the three phases we have. So if these loads are balanced, so we can call it, or we can just denote it by that, or we can write that this balance load is having an impedance of zy per phase. So this zy can be 10 plus 2j ohms per phase. So it means that all these VA, VBN, VCN, or Z1 equals to Z2 equals to Z3 are equal to 10 plus 2J. And I'm talking it for as an example. It can be any complex value of this impedance as well. Okay. So similarly, the loads can be connected in delta, and a balanced delta load is again the same. ZA is equal to ZB equals to ZC, and similarly phase A equals to phase B equals to phase C. Remember, in which the phase impedances are equal in magnitude and phase. So the phase in delta, the phases are delta case, phases are AB, BC, and CA. Remember, there is no neutral wire or neutral conductor, and therefore there is no AN phase. So the phase in delta is between these two lines AB, BC, and AC or CA. Okay, and if these loads are equal, so they can be simplified as Z delta, and that Z delta is again per phase. So phase of delta is a little different than a single phase of Y. So in Y we can have line to line. So this is line to line, and we can have single phase, right? So between line A and B, we can have line to line, and we can have a single phase between line to neutral, or we can also call it as line to neutral. And this line to neutral is the phase in case of a Y connected load or in a Y connected source, both. So the phase is generally between line to neutral, and line to line is a different case. So line to line will have Z1 and Z2 appearing together, and similarly BC line to line will be Z2 and Z3 coming up together. So the impedance will be different in case of line to line, and same if we are talking about voltage, the voltage will be same different. But delta do not have a neutral wire, so the phase of delta is the same as line to line. It is similar is as line to line rather than line to neutral, because there is no neutral in delta. And this is the way this convention works. So this is these are two phases, line to line, and this is another one. So these are some of the differences between a delta and a Y connected loads and sources as well. But again, the key important thing over here is that both Y and delta are balanced. So if they are balanced, it means that the impedances per phase in both delta and in Y are same, and with same it means that they must be equal in magnitude and in phase. Okay, so then the interconvertibility. So delta connected loads can be transformed into Y connected loads and vice versa. So if we have a delta connected load and we have a balanced delta connected load, so remember, this conversion is much easy for balanced load. If we have an unbalanced load, then this conversion is not that easy. It becomes a little tricky. But this generally, the case is that we go for these conversions in balanced loads. So delta connected load can be transformed into a Y connected load and vice versa. So if you have a delta connected load, the impedance in Y, whatever your impedance, say for example, if you have 10 plus 2J as your ZY, your Z delta will be 3 times of 10 plus J2. Okay. And similarly, if you have delta, Z delta is 10 plus J2J, your ZY is less. So remember, if we are converting a Y connected load, your delta impedance to a delta connected load, your impedance per phase will increase. And similarly, if you are converting a delta connected load to a Y connected load, your impedance per phase will decrease. So now there are 4 possible combination of connections between a source and a load. So source can be connected in Y and a load can be connected in delta and Y. Similarly, a source can be delta and a load can be either Y or delta. And similarly, again, for a delta connected load, it can be either Y or delta. But so again, in our practical power systems or in our daily normal scenario, all or any of these combinations come in play. But remember, the most common convention is that the delta connected loads are common. Loads are generally connected in delta, and balanced Y connected or Y connected sources are more common in the uh, you can say in the industry or in the normal common power systems we have, or the the power that is coming to our homes from different generating stations. This is something that is more preferred or is mostly seen across. So generally when you'll go and see or dig deep into these conventions, you'll see one thing, that for delta connected loads, generally the harmonics are trapped inside this delta connected load, and this is one of the advantages of having a delta connected load, that these harmonics do not come out of the load and go into the system. So these are some of the ways in which why these certain combinations are taken up by the engineers and developed in the form of certain standards for power distribution, power transmission, and the other three-phase or polyphase circuits that are practically used by industry or domestic consumers. So now let's solve an example, and this is example 12.1 of our textbook. It says determine the phase sequence of the set of voltages. So we have three different voltages in time domain given to us. VAN is 200 cos omega t plus 10 degree, VBN 200 cos omega t minus 230 degree, and VCN cos omega t minus 110 degree. So first thing, we have to make phasors. So if we are going to make phasors, so we become VAN equals to 200 angle of plus 10 degrees. Then VBN is equal to 200 angle of minus 230 degrees. VCN is 200 angle of minus 110 degrees. Okay. So these three voltages are given to us. So now let's draw a phasor diagram of it. So let's say this is, first of all, whenever you are going to draw the phasor diagram, determine your x-axis first, and from the x-axis draw. So this is my x-axis. Okay. My first angle is VAN. So VAN is 10 degrees apart. So let's say this is my VAN. Okay. Then VBN is minus 230 degrees. So VBN is, if I go somewhere from here, so it will come up something over here. So VBN, so minus 230 degrees from here to here, basically minus 230 degrees. Okay. And then VCN is minus 110 degrees. So minus 110 degrees. So if I'm going to so plus 10 and from plus 10, so go to minus 110. So it is somewhere here. So this is VCN. Okay. So now what will happen? So with respect to x-axis, so this is minus 10 degrees. So minus 110 plus 10 is, yeah, oh sorry, 110 plus 10 is 120 degrees. Similarly to this angle is 120 and this angle is 120. So now what is the phase sequence? So number two, phase sequence. So for phase sequence, always once you have drawn this vector diagram, always uh, part A, draw phasor or vector diagram, phasor slash the vector diagram. And so once you have drawn that, rotate counterclockwise or anti-clockwise, and Number 3, mark the crossing of x-axis by the phasors. So first of all, if it's rotating, say first x, if we are rotating here, C vector will cross x-axis, then B vector will come, then A vector will come, then again C will come, B will come, A will come, then C will come, B will come, A will come. So it is something like this, C, B, A, C, B, A, C, B, A, C, B, A, dot, 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 and keep on rotating because this is a continuously rotating system. So we have a combinations from A, C, B. Again, we have a ACB, we have a ACB. So ACB is a, remember, ACB is a negative sequence we have. So this ACB is a negative phase sequence. So for this case, the phase sequence, to determine the phase sequence, so phase sequence is negative phase sequence. Okay, so whenever you are given any vectors, just follow this mechanism. Draw the phasor diagrams, start rotating the vector counterclockwise, and see which vector is crossing x-axis at first, and then write down this pattern, and then you'll have your phase sequence with you pretty easily. Okay, then comes another question. So this is a practice problem we have. So in this practice problem, we are given one phase, that is VBN, and we are required to find VAN, VCN, and we are told that we have to assume a positive phase sequence. So let's say, first of all, first case is draw the phasor slash vector diagram. So if we are going to draw this diagram, first of all, determine the x-axis. So this is our x-axis. So with respect to our x-axis or reference axis, my B is 30 degrees. So it's not exactly 30, it's more than that. So let's say the 30 degrees for B is something like this. So this is my VBN, and this is my 30 degrees from here. Okay, so my sequence is ABC. So ABC means that first A vector will cut x-axis, then B will come, then C will come. Okay, so if B is here and I am rotating in this fashion, what is the next vector that would be coming to cut this? So this will be the C vector. So my C vector will be the next one somewhere here, and B A vector will be somewhere here. Okay, so let's see. The angle or the phase difference is or should be 120 degrees. So VB is 130 degree up. So the overall between B and C should be 120. So 120 should be from here. 30 minus 120, this is 90. So VC would be somewhere here. This will be VCN, and this angle will be 90 degrees, and this whole angle will be what? So this will be 120 degrees between here and here. Okay, so this is my VCN. So VCN is what? 110 angle of so this is either minus 90 or 110 angle of plus 270 degrees. Okay, so it is up to you how you're going to write it. Again, a good engineer will go with this value. Now A, for A, the angle between BN and AN is 120 degrees. So AN is somewhere, oh, sorry. So AN is somewhere here. So AN, so VAN somewhere here. So 30 degrees plus 120 degrees. So this whole angle between here is 120. From 0 to VAN will become a 110 angle of 150 degrees. Okay, or you can also write as 110 angle of 150 minus 360. So this becomes what? Let me calculate. Uh, it is minus 210 degrees. You can also call it minus 210 degrees. So again, a good engineer will go with these values. So now VAN, again 110 angle of 150 degrees, VBN 110 angle of 30 degrees. This was given, and VCN 110 angle of minus 90 degrees. So this is our answer. So this is how we calculate, or we find out the values of AN, CN, uh, or using the information about a single phasor and the phase sequence given to us. So here I conclude this lecture for today, and see you next time with some more interesting examples for a three-phase circuit. Thank you. Thank you very much.